In this video, we are continuing on with part 2 of our unit on frontiers in data science. This particular one is natural language processing. How might we go about thinking about turning language into data that computers can do things with? We'll do a little bit of a background on natural language processing first. First thing I want to say, NLP, I'll refer to it as NLP, natural language processing. It is not neuro-linguistic programming, which is what I tend to get when I Google NLP thinking I'm going to get to what I'm thinking of. NLP has been around in some form since the early 1900s, though not explicitly called natural language processing. Super interdisciplinary, which is one of the reasons I think it's so fascinating. It's certainly a big part of artificial intelligence, where we ask things like, can computers learn, like reproduce and generate language? Can they understand language? It gets to be a deep philosophical question very quickly. It's part of machine learning. So statistics, neural networks, deep learning techniques are all part of natural language processing. And certainly related to linguistics, it's used in linguistics, it reflects linguistics research. You might be thinking about topics like the structure of language, the representation of language, measuring the evolution of language, how language relates to the brain, and vice versa. And my own area of research is social science. My colleague Arthur Sperling calls it language is an observation of a latent variable. And so if I want to understand, for example, a person's beliefs, their ideology, or their culture, the language they use may be a visible manifestation of an underlying thing that I cannot observe, their beliefs. And perhaps we might be able to use that to do things like explain or predict human behavior. So lots and lots of applications of NLP outside of the kind of chat GPT and bots that we maybe are more used to interacting with. It's also part of the humanities. I don't know a lot about the humanities, and I apologize for that shortcoming, but it certainly is something that is a tool that we can use to understand things like language use, culture, symbolism. So some of the many activities of natural language processing, we might do text classification, so determining what type a text is. An example of this is research that says, hey, here are all these news articles from the New York Times for the last 100 years. You tell me, computer, if these are opinion pieces or sports articles or what have you. A really interesting area that has really made a lot of progress in recent years is topic discovery and modeling. So reading is old. No one needs to read anymore. Instead, we can give our text to computers and they can say, hey, this is about this topic. This is about that topic. There's a lot more to it than that, and it's not quite so bulletproof, but it is a really interesting area of work. Sentiment analysis is a pretty commonly used application of natural language processing. This is where companies, for example, might say, hey, I have all these product reviews. Are they generally positive or negative? Or what is it that they're upset with me about if they're all negative reviews? Document summarization. I have yet to be particularly impressed by document summarization. ChatGPT sometimes, but you could use NLP to create a synopsis. It's absolutely a tool behind any speech to text and vice versa, text to speech conversion and machine translation. I am old enough that I remember the good old days when Google Translate was hilarious. Now it's pretty reliable, which is both useful and not as fun. Here are tons of different applications of natural language processing and why we might go through these exercises. I won't walk through them here. I just mostly want to illustrate that there are tons of applications of natural language processing, not just interacting with ChatGPT. An area of natural language processing that I am most familiar with, and actually was my entryway into data science from political science, is known as text as data. The idea is turning text, words from humans, into data that computers can do things with. In order to get computers to read any text, they need to consume it as numbers. So I thought, to build some intuition, we would look at just how we might go about turning a body of text into some numbers. And it's worth thinking about what's lost or gained by doing so. So here's text, and we want to, this is technical diagram, turn it into numbers. All right, that's what we're going to do. Okay, so the general order of operations, turning text into data. Step 1, have some text. All right, step 1, have some text. This could be existing text. I have a stack of books that I want to analyze. Maybe I find new text. I'm going to download all the articles about Taylor Swift. Maybe I'm going to scan a bunch of physical books from an archive. Maybe I'm going to record people speak, whatever it is that I'm doing. Step 2 is pre-process. This is sort of like the data cleaning stage. We're pre-processing our text so that it can make sense to the computer. And what we're going to do is clean it up for analysis. So we're going to do things like remove capitalization, possibly. Maybe we'll get rid of punctuation. Maybe we'll get rid of something called stop words, which are commonly used words that perhaps don't have much meaning. Then we're going to turn our text into numbers. We're going to use something called the bag of words assumption, and we're going to form something called a document term matrix. Then we'll do some kind of analysis. In the text as data example, and what I do a lot of the time is I'll say, hey, how similar are these two texts? How similar are all the inauguration speeches from all US presidents? Can we cluster them by, oh, these sorts of presidents presidents tend to talk about this. These sorts of presidents tend to talk about that, or they have this speaking style or that speaking style. Is it just based on time, or is there something else potentially interesting going on? How diverse or complex are the texts? There are arguments that political discourse, for example, in the United States has gotten simpler over time. Is that true? Do we care? These are all questions that we could start to think about through this technique. Sentiment analysis that I mentioned before. Some interesting work out there in political science is around bias. Are news outlets, for example, biased to the left or biased to the right? And then the topic modeling that I spoke of before. Finally, we are going to do the inferring. Did we learn something from this exercise? Do we feel like we actually can map all of this back to the real world? All the same kind of inferential questions we might ask with regular old numeric data that we've seen elsewhere. So a little bit of useful vocabulary along with a menacing knife for pre-processing. A corpus is a collection of documents. The plural is corpora. A document is a collection of text. Documents are within a corpus, which is within a corpora. A token is a sequence of characters in a document that are grouped together as a useful unit, such as a word or a number. Type is the number of unique tokens in a document, and tokenization is the act of chopping up a document into tokens. A sentence that recently plagued my life, and I revisit it with some horror, is the sentence, I forgot to order samosas. Well, to tokenize it, I would break those tokens into separate little bits with my fun little knife. So these are my tokens. I forgot to order samosas. I've removed punctuation. I could remove capitalization if I wanted to. Stop words, as I said, are commonly used words, a, and, the, of, etc. We also might want to engage in something called stemming. So reduce words to a root or a base form. So cut off common prefixes or suffixes. There's another technique called lemmatization where we normalize words with the use of a vocabulary. All right, so a little bit more vocabulary. The bag of words assumption is usually the starting point for text as data work. This is the assumption that we make as researchers, and you can tell me what you think about this assumption, that word order in our documents doesn't matter. This sounds wild. It's heresy. The first time I taught natural language processing was in a classroom, and the class right before mine was a course called like literature appreciation. And she asked what I was teaching, and I was like, you don't want to know. Like, we're literally saying, oh, the literature you have, I don't care what order the words are in. Like, I'm no literary critic, but I think the main thing we care about when we say, hey, this author is good, this author is bad, is the order they put the words in. I think that's like the main thing. So we're assuming that it doesn't matter. And we're going to create something called a document term matrix. This is a matrix that describes the frequency of tokens within each document within a collection of documents or corpus. Why? Why do we do this? Well, because maybe we want to calculate something like the similarity between texts. One way in is cosine similarity, which is a metric we could use to measure how similar two documents in a corpus are. And it ranges from 0 to 1, where 1 is identical, 0 is completely different. And turning our text into numbers into that document term matrix will allow us to make that comparison. And by the way, cosine similarity works irrespective of the size of the documents. Mathematically, we're measuring the cosine of the angle between two vectors projected in a multidimensional space. But you already knew that. By the way, I'm going quickly because I want to really just kind of lay out the way of thinking. We have an online free textbook. I don't know if you know about that or if I've mentioned it before, where we walk through this in more detail and give coding examples, mostly from Seinfeld quotes, much to the disappointment and, dare I say, confusion of my students who didn't know what I was talking about. So here's my example for you of bag of words. So this is a sentence I thought of all by myself. The cat wanted to go outside even though it was raining. Literary mastermind. Bag of words assumption says the order of those words does not matter to do the analyses that we want to do. And I know what you're thinking, or if you're anything like me, you're thinking, this is garbage. There's no way we can actually do anything by getting the words all scrambled up. It turns out, and there's been a lot of research to support this, it turns out that it's actually surprisingly robust. Sure, for some work, it doesn't work. The bag of words assumption is no good. And so we keep the order intact. It becomes computationally way more intense, but you certainly can. And there are ways of doing that out there right now that you can explore. But it turns out that bag of words is surprisingly effective. So let's turn some text into a document term matrix. Suppose I have two documents in my corpus. Document 1 says, this is document 1, which is a very good document. Thank you so much. Document 2, with feeling. Our second of two documents is a bit longer and a bit more convoluted, but a lot more fun. Acting without acting. Okay. We're going to tokenize there are 24 unique types and 33 total tokens. This, a, and, bit, but, convoluted. I took all of them, all the documents, both of them, combined them and said, okay, how many total tokens are there? How many unique types? So there are some cases where, for example, the word document shows up more than once, or the word a shows up more than once. That's why we see fewer types compared to tokens. Next, I'm going to remove the stop words, punctuation, and capitalization. I might not always want to do that. You can import lists of stop words, or you can write your own list of stop words, a, and, the. And my idea here is that it's not particularly informative, especially for similarity, whether or not a and the show up in there. We could argue that it is important, in which case we'd leave it in. Think of it as kind of like the same debate you might have about an outlier in a numerical data set. There are reasons to keep them in and reasons to consider our sample without. So now I'm going to do something that sounds complicated, but in fact is very simple. I'm going to create a vector for each document of how many times each term or feature appears in that document, and I'm going to stack them up so they are a matrix. To quote my colleague, Professor Sugars, in the context of unsupervised machine learning, but it applies here as well, what we're doing here is fancy counting. It sounds very complicated. It's fancy counting. Here's what's going to happen. We are going to create a table where each column is a word in our corpus. So across either document, and our words, as we know, are bit, convoluted, documents plural. I've kept those as separate. I could lemmatize or stem those documents and combine them. For now, let's keep it separate. Fun, good, longer, lot, second. Then I'm going to make a row for each document. In document 1, I'm literally going to count up the number of times each one of these types shows up in my document 1. So where document shows up twice, documents shows up 0, fun shows up 0, good shows up once, longer, fancy counting. Document 2, I'm going to do the same thing. We see the word bit, see the word twice, convoluted once, and so on, and so on, and so on. And lo and behold, we have created a data frame, a table of data that the computer knows what to do with. Now, you can see right away, one of the reasons that we remove our stop words is because it would make our matrix that much wider. It's already a very wide matrix, but if we had stop words in, it would be even wider. We'd have that many more features, that much more dimensionality. We could certainly leave it in. It becomes computationally that much more intensive. Another thing to note is that when I talked in the unsupervised machine learning unit about dimensionality reduction, this is a case where we might do that, because in text-to data and natural language processing, we end up with really, really, really wide data sets, and that can be clunky to work with. And so it can be helpful to reduce them to fewer dimensions. But I'm going to leave this here. I really, truly just wanted to give you an idea of how we'd say, hey, here are a whole bunch of words. How do I put it in a format that the computer can work with? Check out our free online textbook for some code for how to try this out on your own. And I am so grateful you were here. And this cat and I will see you next time.